The objective is clearly defined by the marine survey parameters. The target is a submerged FW190A2 designated Yellow 16. The stakes are dictated by a strict environmental boundary and the fundamental limits of material science. The primary goal is to locate the exact coordinates of the fighter and assess its structural integrity before the corrosion-weakened aviation aluminum loses its shape under contact, lifting stress, or a change in support. The physical evidence must be verified without disturbing the fragile equilibrium of the site. In May 2005, the Royal Norwegian Navy vessel KNM Tyr works the coastal waters west of Bergen. The operation takes place in a deep fjord environment, using underwater survey equipment to map the seabed contour and refine a known wreck location. The naval survey pinpoints the target with enough confidence to justify diver assessment. Subsequent visual inspections transition the investigation from a remote sensor contact to a physical target assessment. The divers confirm the wreckage as Yellow 16, the FW190A2 associated with the 12th staffel of Jagersvater 5 Icemere. The aircraft rests at a depth of 196 feet. This depth establishes a hard boundary for access, documentation, and eventual intervention. Bottom time for survey divers is severely constrained by standard decompression limits, dictating that every observation dive must be meticulously pre-planned. The depth also places the airframe in a specific hydrostatic environment. The visual inspection confirms the aircraft is sitting upright and relatively intact on the marine terrain. The initial forensic survey reveals critical details about the condition of the airframe. The visual evidence shows the FW190A2 is missing its cockpit canopy and its fabric-covered control surfaces. The absence of the canopy allows open water circulation through the cockpit, helping internal and external pressure equalize across the main fuselage spaces. The missing fabric on the tail and wings is consistent with long exposure in a marine environment. Over the course of almost 63 years, the exposed cloth and other vulnerable light materials could decay, detach, or be consumed, while the core aluminum semi-monocoque fuselage and the structural ribs of the flight controls remain coherent. The decision to classify this site as a viable preservation target hinges entirely on understanding the specific metallurgical state of the submerged aluminum. The survey teams must determine if the metal retains enough shear strength to maintain its shape. The physics of cold water preservation govern this state, but they do not make the structure safe. The dark, cold saltwater environment at 196 feet can slow some forms of biological and chemical activity. Yet the chloride-rich water continues to attack aircraft aluminum through localized corrosion. The primary metal structure retains its form, but it is contaminated with marine salts and mechanically compromised. This physical reality means the aircraft is not a scattered debris field. It is a single, heavily waterlogged unit resting on the seabed, with buoyancy relieving some effective weight while the surrounding marine terrain carries the actual contact points. The technical problem is the narrow gap between that intact posture and the metal's remaining fragility. Any shift in current or inadvertent diver contact could initiate localized collapse, so the survey remains limited to visual mapping. The environmental baseline is now established. The exact coordinates are locked and the structural condition of the aviation aluminum is mapped within the boundaries of the deep fjord. The intactness of the central fuselage presents a specific investigative problem for the survey teams. Most combat aircraft striking water at high speeds experience catastrophic structural failure, leaving a widely dispersed debris pattern. This FW190A2 did not shatter. The physical evidence of an intact wing root, a coherent main fuselage, and an unbuckled tail section is consistent with a controlled ditching rather than a high-speed crash. How an aluminum fighter reached the seafloor in that condition remains the first technical sequence to reconstruct. The survival of the airframe directly depends on the pilot balancing forward momentum against a sudden loss of power before impacting the water. On December 15, 1943, the operational flight is cut short shortly after takeoff from Herdla. The fighter is equipped with a BMW 801 twin-row radial engine. This complex power plant is designed for high output, but acts as a heavy forward mass if propulsion ceases. Minutes into the flight, the engine develops serious trouble, and the pilot is forced into an emergency landing. The loss of thrust at low altitude strips away most operational margins. The pilot faces a highly constrained geometry. The mechanical breakdown dictates a strict set of flight rules. Without power, the heavy radial engine becomes a major drag and weight penalty, bleeding away the airspeed needed to maintain controlled flight. At low altitude, the critical buffer required to return to the runway is largely gone. Attempting a 180-degree turn under those conditions would increase load factor, reduce stall margin, and risk an unrecoverable departure from controlled flight. The constraint pushes the pilot toward a forced landing ahead on the waters of the fjord. Committing to a water landing in a heavily armored interceptor requires absolute energy discipline. The pilot must trade his rapidly diminishing altitude for airspeed to keep the control surfaces responsive. The water below acts as a hard physical boundary, punishing any incorrect angle of attack. If the aircraft strikes the water nose down, the radial engine will act as a fulcrum, flipping the airframe violently and crushing the cockpit. If the aircraft flares too high, the wings will stall, causing a hard vertical drop that will snap the fuselage behind the seat. The approach requires maintaining a shallow, controlled glide slope directly into the wind to minimize the ground speed upon contact. Before or during the ditching sequence, the cockpit canopy is lost. The FW-190 was designed with a canopy jettison system, and removing the enclosure before impact would have been a logical escape measure. But the wreck alone does not prove the exact moment the canopy separated. The missing canopy is therefore treated as a physical clue consistent with pre-impact jettison, not as direct proof of the pilot's hand action. The airframe makes contact with the fjord surface. A comparatively controlled landing attitude helps explain why the reinforced wing roots, lower fuselage, and main fuselage remain recognizable instead of being torn into a broad debris field. The water strips away forward velocity, but the impact does not destroy the primary structure. The open cockpit rapidly takes on water, stripping away residual buoyancy as the pilot gets clear and survives, later being rescued by local fishermen. With the interior flooding through existing openings and the heavy radial engine pulling the nose downward, the aircraft sinks as a cohesive unit rather than tumbling debris. It reaches the seafloor and settles upright. The intact nature of the ditched aircraft perfectly preserves the physical record of the emergency sequence. With the physical geometry of the intact wreck established, the problem shifts to preventing interference before a heavy lift can begin. The sheer intactness of the airframe immediately triggers a severe operational hazard. Once the location of a submerged World War II fighter becomes known, the site is highly vulnerable to unregulated interference and artifact theft. That depth blocks casual recreational access, but remains within the reach of specialized technical divers. The newly verified coordinates create a strict time constraint. The military assessment team must reduce the risk of unauthorized extraction before a full salvage operation can be engineered, funded, and mobilized. Leaving the aircraft untouched would preserve its archaeological context, but it would also leave high-value components exposed. The dive team therefore applies a targeted securing protocol. Remove easily detached artifacts likely to attract looters while leaving the primary wing and fuselage structure in place. Execution of this protocol requires controlled diver intervention. The primary targets are the mounted weapon systems. The same cold water that preserved the recognizable aluminum fuselage also left the armament identifiable, including the MG-17 machine guns mounted above the engine. The divers descend to recover the weapons as controlled artifacts, treating the work as conservation intervention rather than ordinary disassembly. Steel weapon components and aluminum mounting structures have spent decades in direct contact under saltwater, so the team limits disturbance to the airframe while securing the MG-17 weapons for custody. With the perimeter secured and the physical baseline of the aircraft map, the primary objectives of the initial military survey are complete. The Royal Norwegian Navy concludes its underwater operations at the site. The responsibility for the next phase of the project transitions to a specialized civilian dive team. This handover marks a shift from site assessment and security to heavy salvage engineering. The civilian dive team inherits a highly constrained operational envelope. They are tasked with designing the structural extraction plan for an aircraft that has sat in a saltwater bath for over 6 decades. The removal of the machine guns did not alter the fundamental weight distribution of the waterlogged airframe. The remaining structure is massive, filled with dense marine silt, and completely saturated with water. The team must conduct a thorough physical survey of the fuselage bulkheads and the wing spar carry-through structures. They need to locate reinforced hardpoints that still retain enough shear strength to support the dead weight of the aircraft during a vertical hoist. Every measurement taken by the civilian divers feeds directly into the rigging geometry. They must calculate the precise center of gravity for the flooded airframe to ensure it remains perfectly level during the ascent. If the aircraft tilts nose down or tail down while suspended in the water column, the shifting weight of the internal trapped water could snap the weakened aluminum spine. The divers must route heavy lifting straps underneath the fuselage without crushing the thin lower skin panels. The geometry of the extraction is dictated by a vertical lift of 196 feet and a tightly constrained 5-hour window. The civilian dive team must transition the FW-190A2 from a stable, waterlogged equilibrium on the seafloor to a suspended dynamic load. The primary risk is not the depth itself, but the immense weight of the trapped water and marine sediment inside the enclosed aluminum spaces. The structure is inherently weakened, requiring a flawless distribution of forces. To execute the lift without destroying the airframe, the divers prepare a distributed lifting system around the strongest surviving sections of the fighter. Wide lifting straps and load-spreading gear are positioned to carry the aircraft as a fragile, waterlogged structure rather than as a rigid machine. The rigging must avoid unsupported skin panels, which could buckle under local tension. The system must also prevent upward tension from squeezing the weakened fuselage inward. Once the underwater rigging is confirmed secure, the crane aboard the surface recovery vessel Fleckeroy begins to take up the slack. This initiates the precision hoist. The crane operator maintains continuous, slow upward tension to control the first movement off the seabed. If the winch pulls too rapidly, the drag against the broad surfaces of the wings will exceed the shear strength of the corroded wing roots, tearing them from the fuselage. Conversely, if the lift pauses suddenly, the natural elasticity of the long lifting cables will induce a severe bouncing effect. This oscillation would amplify the stress loads across the main structural spar, instantly fracturing the 63-year-old metal. On November 1, 2006, the heavy lift operation commences in earnest. For the next 5 hours, the crane inches the aircraft upward through the dark water column. The slow ascent is governed by structural control, not by a need to equalize pressure inside sealed spaces. The open, waterlogged wreck is already largely pressure balanced. As the fighter rises through the fjord, surrounding water continues to provide buoyant support while the rigging holds the nose and tail as level as possible. The most dangerous physical threshold of the entire recovery occurs as the airframe begins to break the waterline. As more of the aircraft leaves the submerged environment, buoyant support falls and the suspended weight rises. The seawater and silt trapped inside the internal bays now become an increasing dead load, pulling downward against the lifting straps as drainage struggles to keep pace. At this threshold, the recovery depends on controlled drainage as much as controlled lifting. The crew allows water to escape through existing openings and damaged areas as the aircraft clears the surface, reducing the load before the frame is carried fully into the air. Once the airframe is clear of the water, the boom rotates and swings the suspended fighter carefully over the open deck of the Fleckeroy. The dive team lowers the dripping, heavy frame onto prepared supports. The mechanical extraction is successful, but pulling the aircraft from the water triggers a new, immediate chemical timeline that threatens the entire operation. The moment the dripping airframe rests on the deck of the surface vessel, a severe conservation time window begins. The mechanical survival of the FW-190A2 is secure, but the physical material is now in maximum danger. 63 years of deep saltwater submersion has left the aviation aluminum contaminated with marine chlorides. These salts remain trapped in corrosion products, joints, seams, and inaccessible surfaces where they can continue to drive localized attack. This contamination sets the stage for a critical hazard. When saltwater-soaked aviation aluminum is exposed to atmospheric oxygen and humidity, chloride-driven post-recovery corrosion can accelerate. The damage is not a clean, single-flash reaction. It appears as pitting, galvanic corrosion around mixed metals, exfoliation, blistering, and the formation of white aluminum corrosion products. If left untreated in open air, panels and structural members that look coherent can continue to weaken until their surviving shape is lost. To slow this aggressive destruction, the recovery team immediately changes the wreck's environment. The airframe is rapidly transported to the Håkonsvern naval base, where stabilization can begin. Surface washing is not enough. Prolonged immersion and repeated monitoring are required to draw salts out of joints, seams, corrosion products, and inaccessible surfaces. The intact nature of the ditched aircraft, which was an asset during the mechanical lift, now becomes a logistical and conservation problem. A fully assembled World War II fighter is difficult to immerse and monitor evenly. To save the aircraft, the conservation team divides it along existing joints wherever the structure can tolerate separation, creating 6 to 8 main modules for treatment. The work is not a simple unbolting process. Over 6 decades of galvanic corrosion between steel fasteners and the aluminum airframe have fused many connection points together. Conservators support heavy assemblies before any joint is released. The BMW 801 engine presents the most dangerous handling problem. Its corroded steel mounts require precise external crane support to prevent the massive radial engine from tearing away and crushing the forward fuselage during disconnect. Once separated, the wings, fuselage, engine section, and tail group are secured in specialized transport cradles and moved directly to the treatment facility. The components are immediately submerged in freshwater tanks. Segmenting the airframe allows the team to completely submerge each individual section, initiating the required desalination soak. This necessary procedure leaches soluble salts out of corrosion products, seams, joints, and hidden surfaces before dry storage. By surrounding the aluminum with fresh water, the treatment creates a concentration gradient that allows dissolved salts to diffuse out into the bath. This soaking process requires constant chemical monitoring. Conservators track the electrical conductivity of the water inside the individual tanks. As salt concentrations leave the aircraft, the water becomes less effective at drawing out more contamination. The tanks must be drained, refilled, and tested to maintain the required chemical gradient. This rigorous cycle is maintained for an extended period. The metal is considered stable only when the extraction rate falls to an acceptable plateau, not when every trace of chloride has vanished. Halting the most active degradation allows conservators to finely map the physical history embedded in the individual aluminum panels. With active corrosion reduced to a manageable conservation risk, the stabilized modules move into meticulous forensic analysis. Conservators begin systematic mapping of the airframe to confirm its precise identity while preserving as much original factory primer and internal stencil evidence as possible. One reported work number for the fighter is 5425, but published accounts do not all preserve the number in the same form. As the visual inspection expands across the separated structural components, the physical evidence becomes part of the identity question rather than an immediate contradiction of the historical paperwork. The curators document multiple distinct serial numbers stamped directly into the metal and painted on various sub-assemblies. The tail section bears one set of manufacturing digits, while other structures and accessory mounts may show different numerical sequences. This does not invalidate the historical identity of the primary central fuselage. Instead, it triggers a necessary configuration verification to understand the true state of the machine on the day of its loss. The forensic reality of wartime maintenance means that mismatched subassembly numbers can be consistent with cannibalization, field repair, or pool part replacement in active combat units. Under severe supply constraints, ground crews could move serviceable wings, access panels, or tail sections between airframes, leaving original factory serials embedded inside one operational fighter. This physical evidence suggests that Yellow 16 was a well-used, repaired veteran airframe. By the time it initiated its final takeoff roll from the Herdla airfield, it may already have carried the traces of field repairs and earlier service. The mismatched numbers serve as a physical ledger of maintenance practice, but they do not by themselves supersede the paper flight logs. They give conservators a second record to compare against the archive. The conclusion of the forensic mapping forces a final preservation decision regarding the ultimate physical state of the aircraft. Rebuilding this FW-190A2 into a pristine or airworthy machine would require aggressive structural reconstruction. Original weakened aluminum skins would have to be replaced with newly manufactured metal. Bent bulkheads could be discarded, and mismatched wartime parts could be painted over or standardized. That kind of restoration would risk erasing the exact physical history the recovery team spent months extracting and stabilizing. The chosen route is preservation rather than reconstruction. The aircraft will not be cosmetically rebuilt into a factory-fresh fighter. The stabilized components are carefully transported and reassembled in their original geometric configuration inside a climate-controlled environment. The airframe is mounted on custom-engineered supports designed to distribute static load across the strongest remaining sections, reducing the risk that weakened lower structures will collapse under their own dry weight. The FW-190A2 is placed on permanent, unrestored static display at the Herdla Museum in Norway. It sits in a stabilized condition, preserving the exact structural geometry of its final emergency water landing. The primary objective is complete. The fighter is extracted from the depth, stabilized against the most dangerous post-recovery corrosion risks, and preserved as a verifiable historical artifact under controlled museum conditions.